Okay, so this is very similar to what you guys did in section yesterday. So what we have here, and actually in real life. So we have a string, and we're going to oscillate it with some set frequency mu. And the string has a fixed length, and what we're going to do is we're going to suspend a mass m from its end here. So what I'm going to tell you is that for a given frequency, if I can get 5 antinodes on this string, I want to ask you, if I now increase the mass on the end there to 250 grams, will I have a standing wave? And by that I mean, will we be able to fit an even or a whole number of half wavelengths on that length of the string? And if so, how many antinodes will there be? So it looks to me like people are thinking that the answer is B. Okay, so let's go ahead and work this out. So if we have, I'm going to start with this condition because we have a string that's, we want to find out if we can fit a whole number of half wavelengths on this string. It's the same condition we just worked out. So we know our relationship between lambda, L, and N, where N is the number of antinodes. So if we know that lambda is the speed of the wave divided by frequency, the speed of the wave that we found last time is the square root of the tension in the string divided by mu, the mass density. This is, if I isolate the mass on the end of the string, we know that if it's not moving, if it's not falling, then we know that F had better equal mg. So if we stick these two relationships in here, we get 2L over N had better equal 1 over nu square root of mg over mu. Okay, now if we're not changing the length of the string, we're not changing nu, we're not changing gravity, I hope, and we're not changing our string, if I'm going to move, the only things that are changing are N and M. So if I throw those things over there, I'm going to have N times the square root of M equals, everything else is just a constant. So that means, but for the first case, the number of antinodes times the first mass I put on there should equal to the number of antinodes times the second mass. So if this ends up being an integer, then it looks like we have a resonance condition. So if I put this in there, 3 square root of 90 grams equals N2 square root of 250 grams. Okay, this is going to give me, they both have a factor of square root of 10. This has times 3 is going to equal, did I do something wrong?
Yeah. 5. 3. You have 5.
5.
I have 5, thank you. My why isn't this working? All right, there we go. 5 times 3 equals N times 5. It looks like there's going to be 3 antinodes. Okay, let's try this. Okay, here, for those of you the cheap sheets, let me throw the camera on here and see if this works. Hold on. First, let's see if I can get this thing working. Okay. Awesome. Okay, so this is not a photograph. This is real. Okay, so what I have right here is I have a string that I'm oscillating at about 49 hertz. And I have a mass of 90 grams hanging on its end. And let's see, I zoomed in so you can see one standing wave node antinode right there. If I back up, sorry. All right, let's see if this works. So those who are closer can help me count. We have 1, 2, 3, 4, and 5 antinodes. Okay, so now, let me see if I change the mass over here to 250 grams. Oh. You guys, okay, it's kind of hard to see it there. Let me bring this a little closer. All right. We have 1 antinode right here, the second right here, and a third right there. And if I zoom in with this camera, you can see that right here, the rope really is a node. It's not moving. If I touch it right here, nothing happens. Right here, we have a maximum. And then right here, we have another node. Yay, physics works!